Okay, so in the first part of the talk, we got as far as talking about the definition of latitude and longitude coordinate system for describing points on the surface of the planet of the Earth. So now we'll talk about generalizing that out to what's called the celestial sphere. So the idea is that you project out the lines of latitude and longitude onto an imaginary sphere that surrounds the Earth. And on this imaginary sphere, depending on which direction the star is, you could imagine that the stars are all just stuck on the surface of this imaginary sphere. Obviously, they're not in real life, they're all completely different distances. But in terms of the directions on the sky, you don't lose any generality as long as the stars are far enough away, the objects are far enough away. So you don't have to worry about parallax, that you can make this approximation that it's as though all of the stars are sat on something called this imaginary celestial sphere. And then you can have a coordinate system on that sphere, which is very similar to the coordinate system, the latitude and longitude coordinate system that we have on the planet Earth. So there's the Earth there with the lines of latitude and longitude on it. There's the axis of rotation of the Earth. The point that you get to on the sphere, if you project out the North Pole line, is called the North Celestial Pole, or NCP. The point on the sphere, if you project out the South Pole line along the axis of rotation, is called the Southern Celestial Pole, South Celestial Pole, or SCP. The line that corresponds to where the equator is projected out onto the sphere is called the celestial equator. And then we've got lines similar to longitude and latitude on the sphere, and these are called lines of vice ascension and declination. Right. So the thing to remember is that the declination corresponds to the latitude lines, so moving up and down from the celestial equator, and the lines of longitude, vice ascension, correspond to the longitude lines. Okay, so that's a coordinate system for the celestial sphere, with the North Celestial Pole at the top and the South Celestial Pole at the bottom. Now, if you step outside at night, you're located at some random point on the planet Earth here. So what you'll see is again a spherical coordinate system, but it's not aligned to the main celestial sphere unless you happen to be at the North Celestial Pole. So if you're still at the North Celestial Pole, if all your astronomy was done there, then you wouldn't need to go very much further in this part of the talk. But the problem is that you're going to be sat out here somewhere in Ghana. So you're going to see a subsection of the celestial sphere that is rotated relative to the main celestial sphere. And this is called the horizon system. And it's defined locally for each observer on the Earth, and it's based, and it'll be different for different locations on the Earth, right? So if you imagine, and again, this is all just terminology and words to learn for various things. So we can call the observer's location there with this telescope the origin, and we can define a reference axis, which, as we did before, is some axis around which to do our coordinates. And for that, the convention is just to take the point that's directly above the observer's head. So that's the direction that's called the zenith. So that's the spot in the sky directly above the observer. The reference plane will be a horizontal plane perpendicular to this axis defined by the observer in the zenith. So this green plane here. And then the other bit of terminology is what's called the celestial meridian, which is a curve that goes from the northerlymost point on the horizon here through the zenith to the southerlymost part of the horizon. So if you imagine that imaginary circle around there, that would be called the local meridian or reference meridian. Okay. So this is the key. So within this this system that I've just described, this local horizon system, again, we can define angular coordinates, right? So we can, if we want to describe the position of an object, we can describe something called the alt. So there's the object that we want to describe the position of, say that the star there. We can measure an angle above the horizon, which is called the altitude or elevation. Confusingly, it's got two identical names. And then we can also record a angle starting from the north point around the reference axis, which is called the azimuth. Right. So in this case, the azimuth is measured around here and is probably about 170 degrees or so on this diagram. So the altitude is the height above the horizon, is one way of thinking about it in degrees, and the azimuth is the distance you have to go around the horizon in degrees to reach the point at which the position sits on a great circle that passes through the zenith. Okay, so if you had a telescope, most telescopes have exactly these kind of mounts. They have a mount that swings around horizontally, so an azimuth mount, and then something that can move up and down, which will be an altitude mount. Sometimes these things will have degrees marked on them so that you can actually measure that off. Okay, so that's the sky, if you like, if you step outside into your back garden and have a look at the sky. But the issue is that clearly, unless you happen to be at the North Pole, this coordinate system is going to be rotated relative to the celestial coordinate system. So suppose I'm that point there, looks like the guy is in North America. So there's his horizon coordinate system, which is a little hemisphere there. So there's his zenith, there's his reference point, there's his north, there's his south, west and east parts of his horizon. And you can see that's rotated relative to the celestial coordinate system. So for example, his zenith is pointing in some direction which is not the north celestial pole. And similarly with his other directions, his northernmost point on the horizon is pointing over here, and that's pointing over there. Okay, so what you have to do is imagine two spherical coordinate systems, one of which is rotated relative to the other. So, and going between the two coordinate systems is a very common job to do in when doing practical calculations in spherical astronomy, because you'll look up the position of a star or a galaxy, and that's going to be in the celestial coordinate system, or the equatorial system as it's called, and then so that'll be from a star catalogue, and then you'll want to know where that is in your horizon coordinate system. And this will depend on several things. It'll depend on where you are on the Earth, because obviously the angle at which the thing is rotated depends on where you are on the Earth. And it will also depend on the time of the day, because the Earth is rotating, right? So sometimes, this system is pointing in this direction, but then 12 hours later, the Earth will have rotated halfway around and will be pointing over here somewhere. So this is why, you can you see the sun rise, pass through the sky, and then set, and similarly all of the other celestial objects, the stars and the galaxies, do the same thing. Okay, so let's talk a little bit more about the celestial coordinate system, the equatorial system. So we've seen this diagram before. We've got a line projecting from the rotation axis of the Earth through the north celestial pole, the south celestial pole, and then we have a plane of the celestial equator. And the things that correspond to latitude and longitude lines are called, as I mentioned earlier, right ascension and declination. Right. So right ascension is what corresponds to longitude. So it's rotating around the rotation axis of the Earth, alpha, there. And declination, delta, as it's usually represented, is the angle between the object and the plane of the celestial equator, right, along a great circle passing through the pole. So this angle here, delta. Okay. So let's put some, for example, declination of the equator is 0, in the same way that the latitude of the equator is 0. The declination of the north celestial pole is 90 degrees, and the declination of the south celestial pole is minus 90 degrees. Okay. So the right ascension again is the equivalent of longitude. Similarly to in the same way that that longitude has a reference point, which is the Greenwich meridian I mentioned earlier, the right ascension needs a reference point as well. And this is taken to be where the sun crosses the equator on the 21st of March on the spring equinox. And this is called the first point in Aries, which is because it's in the constellation of Aries. So all you have to know is that there's some line going through the constellation of Aries where the right ascension is defined to be 0. Now, to make it even more complicated, right ascension is normally not measured in degrees. Because the Earth is rotating once every 24 hours, you can actually measure the right ascension thing as though the angle was defined in time between 0 and 24 hours. So 90 degrees would correspond to 6 hours, 180 degrees to 12 hours, and so on and so forth. So this, although it's not time, it's angle. This right ascension coordinate is often given as though it were a time, and that's because the Earth is rotating, and it's often very useful to do that when you're doing practical calculations, because it means that you're keeping everything in units that you can move forwards and backwards in time with really easily. Okay, the celestial equator we've talked about. So that's the projection of the Earth's equator onto the celestial sphere. Now, the Earth is tilted as it orbits the sun. So if you imagine the plane of the Earth's orbit is not at 90 degrees to the north and south celestial pole. It's actually tipped over by 23.5 degrees. So for this reason, so if we're sat on the Earth, it's as if the sun goes around each day or each year in a circle that is inclined at 23.5 degrees to the celestial equator, right? So again, this is so we've now got actually 3 coordinate systems to worry about. We could worry about the celestial coordinate system, which is corresponds to latitude and longitude. We've got the local coordinate system or horizon coordinate system, and then there is the what's called the ecliptic coordinate system, which is, if you like, the central plane of which is given by the plane of rotation of the Earth around the Sun, right? And most of the objects in the solar system move along this plane as well. So if we imagine we're sat on the Earth and we imagine that the Sun is going around the Earth rather than the Earth going around the Sun, it's as if the Sun takes this track here around the celestial sphere. So it goes into the northern hemisphere in the northern summer, and the southern hemisphere in the southern hemisphere in the northern winter. Right? And at this point, if you think about the Earth rotating underneath this, you'll have the same length of day. It's the vernal and what's called the vernal and autumnal equinoxes, which are on the 20th of March. And the Sun, as we said, is in, that's also the special point that's defined for the right ascension direction. So that's 0 hours RA and 0 dec there. The summer solstice will be on the 22nd of June. So the declination of the Sun there will be 23.5 degrees above the celestial equator, plus 23.5 degrees. It would be 6 hours around because we're a quarter of the way around the rotation. It's 24 hours per rotation. We have the autumnal equinox, which is in September the 22nd. And the coordinate of the Sun there would be 12 hours because we've gone halfway around the rotation and we're back at 0 declination again. And then we have the northern winter solstice, which is on December the 22nd. And the coordinate there would be 18 hours, so 3/4 of the way around, and minus 23.5 declination given by the tilt of the Earth's axis. Okay. So in general, yeah, so you'll in the summer you'll have a situation where if you're stood in your in your backyard, in your back garden, the celestial equator will be a curve like this. Again, in Ghana, it's going to be a bit higher than that because it will be probably closer to the equator. And the Sun will be 23.5 degrees above that there. So that's the path the Sun will follow. So the Sun will, in general, in the northern hemisphere, get higher in the sky during the summer, right, on the summer solstice. And then in winter, the opposite happens. So the Sun is now 23.5 degrees below the celestial equator. So the path on the sky will be lower in general on the sky. So it'll be below the 23.5 degrees below the celestial equator as the Sun moves through the sky during the day. And here's just another diagram showing the north celestial pole, south celestial pole, and in the same way you can have ecliptic what are called ecliptic coordinates, which are angles not defined relative to the north celestial pole, but the north ecliptic pole, which is a pole which is perpendicular to the plane of the solar system. And we can define two angles there to measure coordinates in what's called the ecliptic coordinate system. Okay, so let's think about, having said all of this about coordinate systems, what's the summary of the situation? Well, I've introduced 3 coordinate systems now. I've talked about the celestial coordinate system, equatorial system, which has the north celestial pole and the equator. I've talked about the horizon coordinate system, which is the coordinate system that's based on the actual observer, the actual astronomer on the surface of the Earth. And I've talked about the ecliptic coordinate system, which is related to the plane of the orbit of the Earth around the Sun. Right. So let's think about how we might transform between different coordinate systems in general, and how we might visualize what's going on at various points on the Earth and how these things relate to each other. So there is a table here which has some particular observers that might be on various locations on the Earth. So one observer which is on the equator, one who's in the Caribbean, one who's in Canada, and one who's at the North Pole. And this is part of the exercise. So we'll go through some of these now, and then in the exercise later on, you can fill in the more complicated ones. But we'll do some of the simpler ones first to give you an idea of what's going on. Right. So let's start with the observer that's at the equator. Right. So this is this observer in Ecuador. So let's scoot back to imagine what that's going to look like in terms of this diagram. So if you imagine this is the local horizon system for the observer, but the observer's on the equator. So if you imagine this is rotated down now so that this zenith direction will point straight out along the horizon direction, the equator direction. So this thing, imagine that rotated there, right? So that's the central thing to imagine in your mind when you're thinking about this problem. You've got this plane and it's just rotated to various points on the surface of the Earth, right? So what's the first question? The first question is, what is the altitude of the North Celestial Pole? So the altitude is the height above the horizon, and the North Celestial Pole, well, we know what that is. So let's just have a look at, let's just go back to our diagram. So if this is rotated down to there, the North Celestial Pole, which is this direction, that must be just on the horizon, right? If you imagine rotating this around. So this will just be essentially 0 degrees above the horizon if this was rotated around to here, right? Okay, so the North Celestial Pole direction will actually be on the horizon, and it'll be on the northern horizon, right? So let's have a look at it, see whether that's right. Yeah, okay, so that's 0. The altitude of the North Celestial Pole will be 0 because it'll be on the horizon. And again, by the same argument, the South Celestial Pole must also be 0, but it'll be 0 degrees above the horizon, but it will be in the southerly direction. Okay. So this is asking for the altitude of the celestial equator. Okay, so let's go back to our diagram. So imagine this rotated to the equator. Well, the celestial equator is in this direction, and that arrow is pointing towards the zenith, i.e. the position above the observer's head. So the zenith is at 90 degrees above the horizon, so the celestial equator must be, again, at 90 degrees above the horizon, which makes sense, right? So you've got the North Celestial Pole on the horizon in a north direction, the celestial equator directly above you, and the southern celestial pole on the horizon in the southerly direction. Okay, yeah, 90 degrees. Okay, so now let's think about what the declination of the northern horizon is going to be. Now, we just said that on the northern horizon we have the North Celestial Pole in this problem set. So the North Celestial Pole is at declination 90 degrees, right? So the equivalent latitude, if you like, of the North Celestial Pole is 90 degrees. So that will be 90 degrees there. The declination of the southern horizon, well, we said that on the southern horizon we have the South Celestial Pole in this geometry. So therefore the declination of the South Celestial Pole is minus 90 degrees. Okay. And then it's asking for the final thing is asking for the declination of the zenith. So the zenith is the point directly above your head. So if you're on the equator, directly above your head will be the equator, the line corresponding to the equator on the celestial sphere. The declination of the line corresponding to the equator on the celestial sphere will be 0. Okay. So let's do a different position on the planet Earth. Let's think about someone standing on the North Pole, which will actually be a bit easier. So again, going back to the diagram, imagine now that this horizon system is rotated so that it's rotated and this arrow is pointing directly upwards on the North Pole because the observer's on the North Pole. So you can see at this point that the point directly above the observer's head will be the North Celestial Pole. The point that would be directly underneath his feet, obviously you can't see it because the Earth's in the way, will be the South Celestial Pole. So that will be the orientation that we'll be thinking of when we're looking at this part of the problem. So let's have a look. So yeah, the altitude of the North Celestial Pole, well, I just said it was directly above your head, so that's going to be on the zenith, so that's going to be 90 degrees. The altitude of the South Celestial Pole, again, that's pointing directly where your feet are pointing, so that will be minus 90 degrees, so you won't be able to see that. The altitude of the celestial equator, so again, let's go back to the diagram and imagine what we've got there. So again, if this is rotated onto here, then the horizon and the equator line will be parallel to each other. So the horizon line and the celestial equator will be the same line. So that allows us then to, sorry. So yeah, the horizon equals the celestial equator. So therefore the celestial equator must be 0 degrees above the horizon. Okay, so what's the declination of the northern horizon? Well, what is the northern horizon if you're at the North Pole? It's not a meaningful term, but what the declination of the horizon must be 0, right? Because as I said, the horizon equals the celestial equator, and the declination of the celestial equator is 0. Similarly for the southern horizon, right? So any point on the horizon must have declination 0 at the North Pole. Okay, so the declination of the zenith, well, above your head, zenith is straight above your head, you'll have a declination of whatever the declination of the North Celestial Pole is, which is 90 degrees. Okay, so in the exercises later, you'll work out the slightly more complicated cases of someone at a latitude of 30 degrees and 60 degrees. You don't need to do too much of you don't need to do any Python calculations for that. It's just a matter of, making a sketch and then figuring out the angles just geometrically to answer those. But again, all of these exercises are really useful because it allows you to sort of picture for any position on the Earth, where the various parts of the celestial pole will be, so that when you look out at the night sky, you'll be able to say, okay, so the North Celestial Pole should be here, so the pole star should be over here somewhere, and then the celestial equator will be 90 degrees away from that, so that will be a line going across the sky in this direction. So it gives you a nice intuition for the coordinate systems as you're using them. Okay, and again, here's another diagram of what we've seen. So because of this rotation, as that horizon system rotates around the Earth, depending on its latitude, this is what the two coordinate systems look like in general. If you're in the northern hemisphere, the north celestial pole will be somewhere above the horizon. If you're on the North Pole, it'll be at the zenith. If you're somewhere else, it will be at an angle equal to the latitude above the horizon direction. And again, if you sketch that out, you can see why that is. So that's the position of the North Celestial Pole is just equal to the latitude. And then once you know that, then you can work out what the angle of, say, the celestial equator is, because there's 90 degrees between the North Celestial Pole and the equator. So for example, the maximum altitude of the celestial equator will be 90 degrees minus the observer's latitude, just by the fact that there's 180 degrees from north to south there. So you can just use simple geometry to work out these angles using a diagram like this for each of those other cases in the exercise. Okay, so let's leave it there for video number 2. Thanks.